Hello. Today we'll discuss which is on scanning electron microscopy. This is a continuation of the last two modules, which were also on scanning electron microscopy. And in this module, we'll be focusing more on the compositional analysis and compositional contrast generation that can be done in SEM. As usual, I have prepared some questions which you all can look at after this session ends. So these are the questions. Now let's go to week 8 content. But before that, there was a doubt which was posted on the discussion forum. It was related to how the diffraction beam is selected when we are doing TEM for doing dark field and bright field imaging. Yeah, the question was on this. So Shibayan sir had explained that in case of this example, where we have a particular specimen, give me a minute. Yeah. So let's say we have this specimen, and this is the image we can see in TM when we have not put any aperture. But when we look at its diffraction pattern, it is something like this. Multiple diffraction spots can be seen, and there is one central spot given by the orange dot, the orange circle. And Shibayan sir explained that we can choose different diffraction spots or the bright spot also, and for each of those beams, either the diffracted beam or the transmitted beam, we can form an image. For the transmitted beam, we'll be able to form a bright field image, and for any of the diffracted beams, we'll be forming dark field images, right? So D and E are two dark field images, and C is the bright field image. And it was also discussed in the professor's lecture why we get these kinds of contrasts, some bright regions and dark regions, what could be the possible causes for it. But the question posted in the discussion forum was how is the diffracted beam selected so that such a imaging can be done later on. So basically, how do we select a particular diffraction spot, right? For that, we'll have to look a bit into the mm, components of TEM and their arrangement. Okay, so let me explain it. Okay, let me use this image to explain it, which is of dark field in TM. Mm, Let me use just this image here. So here we have this objective lens, which is just below the specimen, and the purpose of this lens is to converge the beam, which is coming from the specimen after being diffracted or transmitted to the specimen. So it is converged, and as a result of this, uh, the diffraction spots form on the back focal plane, where all the beams converge and intersect with each other. So this is actually the back focal plane, and then the image which is formed using those beams, it will form somewhere here, where you will have the image plane. So when we want to choose any particular diffracted beam, what we do is we mm, uh, we first put a selected area aperture strip to select the region in which we are interested. So this is put in the image plane, and once we have selected the region of the specimen which we are interested in, we can then switch to the diffraction mode, where we'll be looking at the where we'll be looking at the back focal plane. So this is the back focal plane, and in this diffraction mode, we'll be able to see a picture which will be similar to what we could see here in B. So we'll be able to see diffraction spots of this kind due to diffraction occurring when the incident beam of electrons is going through the material. And once we have all these diffraction spots, we can then place a objective aperture in this back focal plane itself in such a way that the spots which we are interested in investigating, or the diffracted beam or transmitted beam which we are interested in investigating, only that is allowed to pass through, while all others are blocked. So basically, objective aperture is a small hole that is inserted in the back focal plane in such a way that it only allows certain diffraction spots. It is only allowing certain beams to pass through, and all others get blocked. So in this way, any particular beam of our interest can be selected, and then we can image the then we can look at the image which is formed for that beam only. In this case, we by selecting different beams, we are forming either bright field image or different dark field images. So I hope this will answer the query that was put forth in the discussion forum related to how to select the diffraction beam when doing TM. Now let's go back to session 8. We'll do a recap of the contents. Then in the last 30 to 40 minutes, I'll discuss on the assignment for module 8. Let's look at what we had covered in week 7. So there we discussed on the detectors that are present in SEM, the different kinds of detectors, and what are the mechanisms involved in the detection. One important one was Everhard Thornley detector. Then we looked how SE detectors and BSE detectors can be different, and different principles by which detection happens for both, or the differences in the detectors for each of these. We looked at in-lens detector, and then we covered scan coils and their uses for scanning on the specimen, backscattered electrons. So here we have the in-lens for much better SE detection. Scan coils, and what is the relation between the pixel size and the resolution you can obtain, right? Then, sorry, my bad. Hmm, we were here. Then we looked at detail on how the imaging occurs, how the pixel size can affect, then the effect of working distance and uh, angle of convergence on the depth of field. Yeah. Then we slightly touched upon chemical compositional analysis, ultimate resolution. Ultimate resolution is the smallest probe size which can provide an adequate signal from the specimen. So this will also be looked at in module 8. Then what is the final probe size, which we'll get if we consider all the different effects due to aberrations, diffraction limitation, due to the lenses, due to the mm, uh, lens arrangement in SEM, and in what conditions we can get high resolution, and what are the conditions for getting a high depth of field. Mm. In module 8, now we'll start with compositional analysis. So analytical detectors which are utilized in SEM. First, first EDS detector was covered. So EDS stands for energy dispersive spectroscopy, and why the name is so you can understand by looking at the principle that is used to do the detection of elements. So when it comes to characterization or compositional analysis, the most reliable signal that you can use, which is generated by ACM, is the characteristic X-rays generated from the specimen. And almost all the popular or most commonly uh, used techniques in SEM for compositional detection use characteristic X-rays only. In case of a EDS detector, we have a semiconductor, piece of semiconductor. When the high energy characteristic X-rays are falling on it, due to certain hole pair interactions, what happens is that some current gets generated which is proportional to the energy of the X-ray which falls on the semiconductor. And by measuring the even though the current value of the current will be very small, by measuring it accurately after amplification, it is possible to determine the energy of the X-ray which was detected by the semiconductor. And by knowing the energy of the X-ray, we can then relate it to the element from which it must have been generated, because we know that these characteristic X-rays are fingerprints of the elements from which they get generated. Since they are directly related to the inertial excitations which occur in the atoms when the incident electron beam falls on them. We have already seen inertial excitation and how it occurs in detail in the previous lectures. In case there are any doubts, you can let me know by unmuting your mic. So the uh, advantage of using EDS is that it can be used to detect almost all a very big range of elements at the same time. But there are some limitations also. One limitation is that it cannot detect the, okay, we'll come to that one later. So one limitation is that you need to have a very a detector which can very quickly detect the X-rays and convert that into a current which will then be detected to be able to find the energy of the incident X-ray. So this usually takes some time, and you need to have a good detector if you want to do it in a short time. Otherwise, you might be missing some of the signal when you are doing the scanning. Another limitation, so the second limitation and the major one, is that it is very difficult to detect the lower atomic number elements using EDS. The reason for this is that these lower atomic number elements have a lower energy characteristic X-ray. So due to the low energy of these X-rays, it is there is a higher chance that these X-rays will get absorbed in the beryllium or carbon window that is present in the detector. And as a result, the detected value of the current might not actually be accurate. So it is difficult to quantitatively measure the lower element percentages by using EDS. So also there are a pure SI is not used in these detectors. There are some variants of SI which are used so that you can generate more electron hole pairs and more current gets generated to make the measurement of the current easy. So these things are in the slides and the lectures. You can go through them if you want to know in detail. So as I was saying, the whenever a X-ray falls on the detector, there is a process that has to electronics related process of generation of electrical pulse that has to occur, and then once that pulse is generated, it is amplified, and sorted. That is, it is measured, and after that the next signal from the X-ray can be taken. So there is a limit due to the processing speed of the detector. So because of this processing time that that will be because of this processing time associated with the detection of every pulse, there is some time which is called dead time, which will occur, and then there will be some time which will be called lifetime, which involves those times when the uh, detection is happening. That is the time for which the detector was counting. But there was also some time where the detector was not counting because it was processing the earlier registered pulse, earlier registered X-ray, and that is the dead time. So this was how EDS works. But then there are certain limitations. Two of them I have already told. Another one is that the resolution of EDS is very low, so the peaks can get fudged together, and resolving the peaks is difficult because the so resolving the peaks is difficult, as can be seen from this example of the same specimen for which EDS was done. Then another technique called WDS was used, and in case of WDS we can see that the peaks are much more sharper, so it is possible to pinpoint different elements or phases present, which was not possible in case of EDS. Also, how is the percentage of element calculated in case of WDS or EDS? That is done by just mm, measuring the intensity of the X-rays which are detected. So the energy of the X-ray which is detected will give information related to which particular element it came from, but the intensity or the number of counts for that particular X-ray frequency will give information which will be related to what is the percentage of element or a percentage, let's say, of a element in the specimen, and using that we can get a idea of the composition of the region from where the scanning is done in the specimen. Now let's look at WDS. WDS stands for wavelength dispersive spectroscopy. In WDS, we have a analyzing crystal and a X-ray detector that can detect any X-ray uh, which is reaching it. And here, uh, the despacing of the analyzing crystal is known, and it is positioned in a particular fashion. So there is something called Roland circle on which the specimen and the detector are kept. So actually, specimen, crystal, and detector all fall on one circle, and the reason for this is that we make use of the phenomena of diffraction. We know that diffraction only occurs at particular angles, which are given by Bragg's law, and lambda equal to 2d sine theta, and this is made use of in case of WDS. So if we have a crystal kept in between the specimen and the detector, and the electron beam hits the specimen, some X-rays will come out from the specimen, which will reach the curved crystal, and depending on whether the conditions are favorable based on Bragg's law, it is possible that constructive interference can occur, and there will be diffraction by an angle to theta. And if the diffraction occurred and the detector could detect the X-ray, then on the basis of that, it is possible to determine what was the lambda or the wavelength of the initial X-ray which came out from the specimen. And by changing theta, we can detect the different X-ray wavelengths which might be coming out of the specimen. And then finally, by looking at the number of counts which were detected by the detector, we can then quantify what was the percentage of all the elements from which X-rays were generated. So the major advantage of this is firstly, as shown here, that since we are using single crystals of known d-spacing, the quality of the results we get is much higher here. The different peaks that we measure are much more sharper, so it is possible to get uh, more accurate um, information regarding the composition of the specimen. But the limitations are that firstly, you require different detectors for detecting different range of X-ray energies or X-ray wavelengths. Secondly, though the detector can usually count at high rates, there are some uh, though the detector counts at high rates, because of the geometry of this setup, the amount of signal that can be collected is very low. The solid collection angle is low. So because of this, detection becomes slow, or the detector efficiency is low, and as a result, it requires more time to carry out WDS. Also, as I had said, that one particular crystal can only detect can only be used to detect a certain range of X-ray wavelengths. So for detecting different elements, we might require different crystals. If you already have some prior information about what the composition might be or what might be the possible elements in the specimen, you will have to use corresponding correspondingly different crystals which can detect the X-rays coming from those elements, and doing this can take more time. Also, there is one limitation related to signal dilution because of multiple orders of reflection which can take place. The major advantage of WDS that is that even light elements can be detected fairly accurately, and quantitative measurement is uh, much more accurate in case of WDS. In in case of EDS, these two things are not possible. Accurate measurement is very difficult. So WDS is preferred. Now that I have discussed EDS and WDS, which are the two main methods of analytical spectroscopy, we'll again get back to imaging in SEM. How imaging occurs. We have already seen the rastering process and the process by which the scanned area on the specimen can be brought onto a screen like this, and in real time both the scanning on the specimen as well as the formation of the image pixel by pixel on the monitor of the screen display screen can take place. Now we'll start looking at contrast formations in SEM. Hmm. In this example, we can see region in a specimen where I see the image formed by secondary electrons and backscattered electrons are shown, and there is a difference in the topography or the so type of topography is the same, but the contrast of the different features in both can be seen to be different, right? This shows the backscattered electron image. If we use the Z contrast mode, now let's see how contrast formation occurs when we are using either secondary electrons or backscattered electrons for doing the imaging, because it is important for us to be, when we are doing SEM for some purpose of investigation, to be able to resolve the features well and be able to accurately depict the features as they are in the sample in the image also, so that there is no loss of information or addition of false information in the image. So that is the reason we'll try to understand how contrast formation occurs and how we can use that information to produce better images when doing SEM. Let's say we have a specimen and we are scanning on it. So based on the topography, I've already, I think, touched a bit upon how topography can influence signal generation in SEM for both secondary electrons and backscattered electrons. So based on the roughness or the protrusions on the surface, different amount of electrons will come out as you scan on the specimen. So if the signal you get is something like this or this, there are some peaks and then there are some valleys. It is possible to quantify the contrast based upon the peak value of the electron secondary or backscattered electron intensity. So we can use the peak value as well as we can use the mean value of the signal that is coming. And based on the difference between both of these, we can say that the contrast will be proportional to this difference. We can define it something like this, where this is delta is the difference between the peak and the average value, that is the background, and S max is the total intensity of the peak. Now, when we are talking about contrast, we basically want to eliminate the effect or reduce the effect of noise in our images as much as possible, so that we can get useful information from about the specific characteristics of our specimen. So in case of a signal like this, we can, if the number of electrons that is getting detected is n bar, to say that it is an average number. So if it is n, then the square root of it will give the value of noise. So the reason that we are taking a square root here to quantify the noise is that this is a very statistic process, stochastic process. A lot of randomness is involved, and on an average, the amount of noise that will occur in case of these kinds of measurements tends to be root of the total amount of signal that is received. So for example, in this image we can say that this is our signal while all of this is our noise. So from just understanding this, we can say that in order to get more like lesser fraction of noise, we need to have a larger number of electrons which are reaching the detector, that is n should be large. Our human eye has a limitation that it can only distinguish between 2 points if the noise value is less than a certain value. So if the contrast or the difference between the peak and the background is 5 times more than the amount of noise, only in that case we'll be able to resolve 2 points clearly. Otherwise, our human eye will not be able to resolve it. So now, since we know this limitation of our eye, we can use this. We can combine this with the definition of contrast value and the value of noise we know as root n. And when we combine it, we come if we want to be able to resolve between 2 points, then we can get this equation: S max equal to n bar should be more than 5 by c square. So for a particular value of contrast, the amount of signal that is detected should be more than 5 by c whole square in order to be able to resolve the 2 points well. So this gives us a lower limit of the amount of signal which is necessary to be able to uh, observe a particular contrast level. Also, we can then also incorporate the number of electrons coming from the specimen, the time taken to scan the specimen, and also the efficiency of the detector. And when we combine all of this and plug in it into the previous equation, we can then tell what will be the value of the number of electrons detected based on the different characteristics of the detector, the specimen scanning rate, and the number of incident electrons. Using this, we can then calculate the minimum probe size which will be required to be able to observe a particular contrast level for a given frame rate. So frame rate is nothing. Frame rate is related to the rate at which at which an image is formed. So, for example, in case of televisions, we have a particular frame rate which tells us that one frame or one image takes this much time to form, and the lower the frame rate, the more the number of images that are forming for a particular time interval. Right? So the higher is the frame rate, the more are the number of images forming, and the more coherent the whole video will look if you have a higher frame rate. But it also means that if the frame rate is very low, the scanning is very fast, and we are able to take in much less signal if the scanning is fast. If the frame rate is very high, that means we are giving the detector a lot of time for making just one image. Scanning is very slow, and as a result, since we are getting a lot of signal through electrons, the image quality, that is the amount of noise that is there, that will be very low. It will be a very clear image, and therefore if we look at lower frame rates for a particular contrast level, let's say zero point 0.5, very low incident current is required for being able to view this contrast level. But if the frame rate is very high, that is scanning is very fast, then the detector is not getting enough number of signals to be able to generate a good image, and as a result, more number of incident electrons will be required to be able to see this same contrast value of zero point 0.5. Also, I hope you all can understand that the minimum probe size is directly connected to the amount of to the number of electrons that are incident on the specimen. So it is directly proportional to the specimen current, you can say. And here we have a formula for it. So if you remember from the previous lectures, alpha naught was the convergence angle just when the beam came out of the condenser, and alpha 1 was the angle at which it entered the objective lens. And because of there being an aperture placed just above the objective lens, a lot of the beam gets blocked. So the smaller the aperture will be, the smaller will be the alpha 1 value, and the smaller will be the amount of current that will be going through the objective lens, and as a result our probe size will decrease. and this decreased probe size will uh, correspondingly also mean that we have a smaller specimen current, that or the less number of electrons are reaching the specimen. So the main takeaway from all this conversation and discussion on contrast is that along with the different sources of aberrations and limitations to or sources that can cause increase in the probe size, which will lead to reduction in the final resolution. There is also this contribution due to the amount of signal that is reaching the detector. If the amount of signal reaching is too low, that will mean that a lot of noise is there, because of which also resolution will decrease. So there is something called ultimate resolution, which was also covered in week 7, which also accounts for the contribution due to contrast. And if the contrast level is low, then the resolution will be poor, the size of the probe will be higher. And if the contrast level is good, it's high, then the resolution will not really be affected due to this, and it will be good. I hope I am clear. Things are clear with regard to contrast generation and contrast values. Now let's get into topographic image. We have seen these two images in the previous slide too, for the SE and BSE detectors. For generating the topographic image, we rely on the characteristics of the surface, that is the protrusions that are on the surface or the valleys on the surface. But how does that affect the generation of electrons, and how is that then leading to generation of contrast in the image? For that, we'll have to look what happens if the electron beam, incident electron beams, uh, hits a specimen at an angle. So we have already talked about this when we talked about the effect of tilt angle on the yield. So when the surface is at an angle which is other than 90 degree to the incident electrons, it is lower than 90 degree, and the interaction volume due to the incident electrons in the specimen is much more closer to the surface. It is much more closer to the surface of the specimen on one side. As a result, the escape depth, which is constant, can easily be reached on one side of the surface. So electrons and other signals find it very easy to just overcome this small depth and come out of the surface. As a result, we see that both BSE and SC yield increase when we are tilting the specimen. And this has direct relevance to the measurement or formation of topographic contrast in the images. So now that we have understood, yeah. So before moving on, let's just connect all the dots which we have already found. So now that we know the effect of tilt on the electron yield, we can use a detector which counts the number of electrons that are reaching it, and for the um, tilted portion, or that is the hills on the specimen, more electrons will get generated, more electrons will get detected, and as a result the brightness in the image for those regions which have hills will be higher, while for the valleys correspondingly less number of electrons will be able to come out, and as a result the they will appear darker in the image. And using this phenomena we can generate the topographic contrast in SEM images. Another aspect to SEM imaging is that the images that are formed are very similar to those which are formed by optical microscopy, which uses light instead of electrons. So even though the phenomena involved in optical microscopy and SEM are quite different, how come we are able to see similar images? So the reason for this is that in optical microscopy we have light falling on the surface like this, and then it is getting diffused and reflected in different directions, and all of the light which gets reflected in a particular direction and is detected by our eye, that is used to form the image of the surface. But in case of SEM we have a parallel beam of incident electrons. They are interacting with the features, they are generating different number of electrons from the surface, and these are then detected. So in both these cases we have a source of either electrons or light, and then the resulting signal that is coming out is detected. And since the topography of the surface has a big contribution to how much, has a big effect on how much signal is getting generated, in both of these cases we see similar image, since topography plays a role in both of these. Now there is also another mode of measurement of topography called topography mode, which uses a stereo microscope. So here instead of just using one detector, we have two detectors. Sorry, we do not have two detectors. So instead of just using one particular image, we tilt the specimen and take another image. Just like in case of our eye, we have two different eyes placed, and we can see each eye looks at the object at a small tilt angle with respect to the other eye, and the image formed individually in both by both the eyes is then combined to be able to form a 3D image. So that is the principle of stereo microscopy. You look at an object from slightly different angles and then use that to be able to construct a 3D representation of it. And by using a stereo viewer, it is possible to get a 3D representation. Now I think we'll contrast between the topographic image which is formed by BSE and that which is formed by SEs. Okay, let's just look at it, then take a 5-minute break. In case of BSc, in contrast to SE, we know that only those BSCs or backscatter electrons which are leaving the specimen at a particular angle, which is in the line of sight of the detector, can be detected by the detector. If the BSCs are coming from some other angles uh, from the specimen, then due to their high energy, they uh, are difficult to be deflected and they do not get detected. So just like in the case of human eye, where only that light which is in the line of sight, which is leaving from the object and is in the line of sight of our eyes, only that light can be detected. Just similarly, in SEM, only those BSCs are detected which are in the line of sight of the detector. As a result, those areas in the specimen from which BSCs, more BSCs are coming out, which are in the line of sight of detector, will produce a brighter contrast in the image, while those features or those regions from which less BSCs are coming, which are in line of sight, will appear darker. As a result, some kind of topography can be generated using BSCs. So, in order to tackle this issue of line of sight of a particular line of sight in BSC, we use multi-element detectors. For example, here we have discussed this also in the previous lecture, that we can have a 4-element disc shaped detector, so that BSCs which are coming at different angles, multiple different angles, that is a higher solid angle range, can also be detected. So as a result of this, so this will be like viewing a specimen with several light sources, and as a result we are able to get better topographical contrast when we are collecting more number of BSCs, that is BSCs coming from higher solid angle. Okay, let's now look at the last lecture of this module. How is the topography that is obtained from a C and BSC image different, and which is better? In general, we observe that the topography is much better from SE image, and it is much more common to use SE images for getting topographical information from a specimen. The reason for this is quite straightforward. The tilts on the specimen can have a larger effect on the SE emission compared to BSE emission, and that is one factor. And another is that SE electrons can very easily be detected at a very high efficiency. So almost all of the SE electrons get captured, while in case of BSE, only those which are in the line of sight can be captured. So because of both of these twin reasons, we SE images are more commonly used for forming for getting topographic information, but it is also possible by using a multi-element detector and certain imaging modes to be able to get a good topographic image using BSE also. For example, this is for single element where you can see lots of dark shadows as well as very bright regions. So from this it is difficult to tell reliably about the topography due to such bright and dark regions. But if you use four segments, then the picture is much more clearer. The topography is uh, clearer in this image. And then if we see SE, then we can qualitatively say that we get a much better 3D representation of the specimen when we look at the SE image. Now, as I told that we can use a multi-element detector for BSE topographic contrast generation. So what exactly it does is, if there are two opposite detectors, let's say this is A, this is B, then any region on the specimen will emit BSE electrons which will reach both A, and some BSE electrons which will reach B. So the firstly there will be an effect due to the atomic number of the elements in that region, but since that effect will be same for A and B, the amount of signal reaching A and B due to the atomic number contrast will be the same. But because topography also plays a role, the BSE electron intensity at A will be different from that at B, and by subtracting the intensity that you are getting at A and B, you can get the topographic information of the specimen, because all the background will get subtracted and only the difference in signals due to topography will remain. And if you use that to form an image, then you will be able to get a very good topographic contrast. So topographic features will get enhanced, and we might see signals images something like these. I'm not sure, this is not a backscatter, this is the specimen actually, but here you can see that it is possible to see get some information about the depth of these features. So that was how topographic contrast can be generated. But instead of that, if we do averaging of the signals which is received on these two detectors A and B, then the contribution of topography will get averaged, or it will not have much of an effect, and the atomic contrast will have a higher effect on the averaged value. So this can then be used to form a atomic number contrast image or Z contrast image. Since here the grayscale value is determined by how many backscattered electrons are reaching the hole of the detector. So one limitation which comes when doing topographic imaging using BSEs is that BSEs have a very high sampling volume, 100 nanometers or less, but in BSE you can have it up to 500 nanometers. Actually, these are the interaction volumes. The sampling volumes will be lower than these. I think maybe it's not mentioned here. Mm-hmm. Anyways, the sampling volumes will for SE will be quite low compared to those due to BSE. It's in few nanometers for SEs and in hundreds of nanometer for BSE. And as a result, for BSE, there will be a limit to the resolution you can obtain when doing topographic information, when doing topographic contrast imaging. Also, one difference which comes when using BSEs and SEs is that BSE is much more sensitive to the atomic number of the elements from which the electrons are emitted or electrons get generated. So the yield due to BSE has a much higher dependence on the atomic number of the atoms in the specimen. It can be seen from this plot, and this can be used to generate a atomic number contrast. When generating atomic number contrast, it is preferable to have a polished sample and a sample which has not been etched. The reason for this you can try to think on your own. It is related to what you are looking for when doing atomic number contrast imaging. So you can think about why the sample should be flat and it should not be etched when you're trying to do compositional imaging using BSE. Hmm. Hmm. Yeah. One limitation when it comes to atomic number contrast imaging using BSE is that if the elements are very close to each other, the contrast will be very low, due to which it might be difficult to resolve between 2 points having two different atomic numbers because the difference is too low. So the resolution of atomic, so the compositional imaging resolution might be low because of this reason. As I told, by adding the signals from different detector elements, you can get you can get a higher amount of signal, and as a result, you can get better compositional contrast. And if you do that, the contribution due to topographic contrast, which is more like a noise when you are trying to detect the composition. So this topographic contribution will reduce, and as a result, we'll be able to get good compositional image resolution. Also, before we end, when doing BSE Z contrast imaging, it is preferred to have short working distances so that a higher solid angle detection region is present. The cone from which in which detection cone of solid angle from which detection happens is bigger. So we prefer short working distances, and also we prefer uh, high accelerating voltage so that BSE generation will be slightly more. With this, the week's content has been gone through. So now we can move to the assignment. But before that, let's just take a 5 minute, 5 to 10 minute break. Then we start with the discussion on the assignment answers. Hmm. Let's start with discussion on the assignment questions. The first question is EDS detector normally consists of. We know that EDS stands for energy dispersive spectroscopy. The energy of the X-rays is utilized for identifying the elemental composition, while in case of WDS, the wavelength of the X-ray has a more important role in the identification of the, though both are connected, the wavelength is used to do the detection. So in EDS, we use some silicon based semiconductors or germanium based semiconductors to be able to generate a current which will be proportional to the energy of the X-ray which falls on the semiconductor. So the answer will be C. Semiconducting elements. Which of the following element is not detected by EDS? We slightly touched upon this, that lower atomic number elements are difficult to be detected by EDS, and because we have a beryllium or a carbon window which is used to protect the elements of the detector, which are very sophisticated and sensitive, they are very expensive also. So since we have those windows made of these low atomic number elements, if there is an X-ray which is coming from a lower atomic number element like let's say boron or carbon, it will get absorbed by the higher atomic number elements which make up the window. So these X-rays generated from lower atomic number elements will not be able to reach the detector. So it will not be possible to detect them by EDS. Boron has a lower atomic number than beryllium and carbon. As a result, it will not get detected. What material is used to coat both surfaces of an EDS detector to apply a bias potential? So I have not covered this, but it was covered in the lectures by Professor Shibayan Roy. In our EDS detector, we use a very thin film, about 20 nanometer thin film of gold, because if because of its very high conduction properties, high conductivity. So both surfaces are coated by a thin gold film. The answer should be AU, option A. Next question: the purpose of the window in EDS detector is. As I just touched upon in the second question, we use a window so that we can use it as a covering for the more sensitive and expensive elements of the detector. So if there is any contamination due to the specimen that is put or due to improper vacuum conditions, then that contamination will not be able to affect the detector elements as much if we have some covering on it. So that is the reason for having a window in the EDS detector. The correct option will be C. Let's also just have a brief look at what was written in the lectures related to this. Here also the same reason has been cited. Hmm. Okay, let's move to the next question. The resistivity of SI and EDS detector is increased by. We also touched upon this in our lecture. So the resistivity can be increased by all three of these routes. By making the hole detector a PIN junction, which is reverse biased, so that the electron hole pairs, number of electron hole pairs that are generated will be changed. Doping with a small amount of Li, and third is cooling the hole detector to liquid nitrogen temperature. I think there might be a typo here, because all of these should be actually increasing the conductivity of it and reducing the resistivity. By doping with lithium, excess number of electrons or holes will be generated, which will lead to an increase in the conductivity. There will be more number of electrons or holes which can act as carriers, mobile carriers. So I think it might be that here they wanted to, sir wanted to say that the resistivity will decrease, can be decreased by these processes, and due to this decrease, more current will flow, like the electrical pulse which will be generated will be higher when the X-ray hits the semiconductor, and because of the higher current, it will be easier to measure it more accurately. So I'll have to verify it, but I think here instead of increase we should have a decreased, and all three options will lead to a decrease in the resistivity. So correct answer is D, all of the above. And question 6, in WDS, what type of signals are permitted to reach the detector? Hmm. We have already covered this when we were talking about when we were talking about the arrangement used in WDS, the different elements which are part of the WDS setup. The correct answer is characteristic X-rays of specific wavelength. Continuous X-rays mm, come due to the outer electron transitions, but these are not very characteristic of the elements. So, and also they have a much lower energy compared to characteristic X-rays, which are from inner electron shell transitions. So these are not these usually are not able to reach the detector. They do the crystals are such that they only allow diffraction of characteristic X-rays. So the answer is B. To obtain the focusing effect in WDS, the specimen crystalline detector must lie on a circle. We have already seen that they need to lie on a circle so that no matter at what angle the BSc electrons are leaving the specimen, they will always reach the curved curved single crystal at the same angle. I'll show it here. So if this is where the BSCs are getting generated from, and if the detector is here, let's say this is the center, then these two angles will be the same. If this is the crystal, this is the single crystal which is curved, these two angles will be the same. Let's call it theta. So no matter at what angle the BSc is the specimen, it will still be detected at the detector. And this circle is known as Rowland circle, likely because it was invented by Rowland. Now, X-ray line broadening affecting the detector efficiency is possible for X-ray line broadening. Basically relates to broadening of the peaks, which is undesirable because it makes it difficult to get the accurate value of the energies of the characteristic X-rays. So broadening will lead to increase in the noise in the signal, and this is more for EDS because it uses a different process compared to WDS. WDS is more accurate. EDS uses some semiconductors and electron hole pair generation, which leads to current formation, and this has a lower resolution and higher noise compared to WDS. Which statement is correct for WDS technique? We have already talked about the yeah, we have already talked about the benefits as well as limitations associated with EDS and WDS technique. We know that in case of WDS, scan time is slower, comparatively slower, because we have a smaller uh, the signal collection efficiency is much smaller, so it takes more time to collect a good amount of signal. Line broadening is less in WDS, but it is not totally absent. There will be some line broadening. Only one wavelength of X-ray is detected at time. Yes, this is true, because for a particular d value of the crystal and a value of theta for the setup, only one wavelength will be able to cause diffraction. So only one wavelength will be detected at time. So our correct answer is C. In case there are any questions, you can just unmute yourself and let me know. Which one is true for the SEBSE images acquired in SEM in 8-bit pixel? Okay, so I think I have not covered in detail what 8-bit pixel or the number of bits means in the pixel. So in short, I'll just say that when you have any display, you have pixels which make up the display, a large number of pixels, and each pixel can have some particular dimensions. Maybe usually it's around 0.1 mm by 0.1 mm. It's a small square. and every single pixel will have one homogeneous color value. In case of gray images, it has a grayscale value. So each of these will be different, and together all of them will form one image. So if we have a 8-bit pixel, it will mean that one pixel can have 2 raised to 8 different values of the grayscale. So value of 0 will mean that it is totally dark or maybe totally bright, and a value of 2 raised to 8, that is 2 raised to 8 minus 1, actually 255, will mean that it is totally bright or totally dark. I'm not sure what is the exact, which one is dark and which one is bright, but these are the two extremes, and in between we'll get different levels of gray. So by controlling this, we can form an image. So this was how number of bits in pixel is defined, and the correct value therefore will be B, 255. Now, the grayscale value of a pixel in SEM image depends on the number of in SEM. We know that we have SEs and BSEs, which are generated from the specimen. These photoelectrons are generated within the detector as a part of the detection process. So they should not have any role to play on the grayscale value of the final image that is formed. Like, we do not want to have any role to play. These are just an intermediary thing which are used. And we know that the grayscale is value is depends on the intensity of the electrons which are reaching the detector. That is the number of electrons reaching. So the correct answer is D, BSE and SE. Next question. In SEM, topographic images are obtained. We have talked about topographic contrast generation using SE and BSE images. The correct answer is A. OJ electrons are very low in intensity, and it is not possible. They come from very close to the surface, but their intensity is very low, and it is not possible to be able to get topographic information using them. BSE signal from the specimen is capable of yielding information about the correct answer will be C, both topography as well as compositional imaging. We have discussed about it in detail when we were recapping. It won't tell about much about the electronic structure, because BSE electrons are generated due to Coulombic interaction with the nuclei of the atoms. They do not have the incident electron does not interact much with the outer electron when it comes to generation of BSEs. So the electronic structure will not have effect on the BSE signal generation, and our answer will be C. In an SEM detection system, the minimum detection current to achieve a particular contrast level is we know that to be able to get a particular contrast level, we mm, Let's go to the slides to look at this thing. Yeah. Hmm. Yeah. So here we need to tell what will be the relationship between the detection current and the frame rate at which scanning is done for getting a particular contrast level. So we know that the frame where we have already discussed this, the frame rate dictates how much signal the detector is able to get from a particular uh, point or region on the specimen while scanning. So if the frame rate is low, means that it is spending scanning is slow, more number of signals can be generated from a particular region, and therefore the amount of signal that is reaching the detector is higher. So if this is the case, the noise is comparatively lower because the noise to signal ratio or signal to noise ratio will increase as the amount of signal increases. So for a particular contrast level, uh, if the scan frame rate increases, we can expect that the minimum detection current that is required will be higher because the scanning is faster. So you need to have more current, more number of signals if you still want to be able to uh, mm, be do the imaging. If you still want to get a good resolution for a particular contrast level, so if frame rate increases, you'll have to have more detection current also, because basically the total number of electrons reaching is equal to IC into T, which should be uh, which should have a high value. But if the frame rate is low, it means that you have much more time, so even a smaller IC will be fine. So minimum detection current will be lower for a lower frame rate and higher for a higher frame rate. Correct answer is C. This can also be seen from the plot corresponding to this in the lectures. You can go back to it and see. The last question in EDS. If there are any doubts related to these, you can let me know. Last question in EDS. CuK alpha X-rays with energy of 10 keV will give rise to approximately how many number of electron hole pairs? Hmm. Let's go to the corresponding slides in the lecture. So here we see that for this silicon based conductor, the energy required for each excitation of electron hole pair or generation of electron hole pair is constant at about 3.8 electron volts. So if we have 10 kilo electron volt X-ray getting generated from copper, it is K alpha X-ray, that is L2K K shell transition with energy of 10 kilo electron volt, then the number of electron hole pair generated will be 10 to 10 is to 3 divided by that of energy required for generation of one pair, 3.8 electron volt. This number will be so this will be approximately, I think, 2500. Exact value we can calculate. Exact value is 2631 pairs. With this, the assignment is completed. In case of any doubts, you can write on the discussion forum, or you can let me know right now. Or later on, if you have any doubts, you can put on the discussion forum in the same way you all have been putting till now. So, can we now wrap up this session? Okay, thank you for attending. I hope this was useful for you all. We'll have the next session next Saturday at the same time, where we'll discuss on module 9. I think it's on X-rays, so this is uh, a new topic that we'll be starting. So thank you for attending. See you next time.